Hello. In this video we're going to talk about precipitation as described in chapter 16.2. Notice that we are going to skip the section on qualitative analysis. Now, in the previous section we talked about the dissolution and dissociation of a slightly soluble ionic compound, and we can write an equation to represent that as follows. Mx dissolves and dissociates to form Mn plus x n minus as governed by the value of Ksp, the solubility product constant, the equilibrium constant for this process. So, what about precipitation? What occurs in a precipitation reaction? Well, in a precipitation reaction, cations, for example Mn+, react with anions, for example Xn-, to form solid Mx. How is the precipitation reaction related to the dissolution and dissociation reaction? Well, as you can see, clearly it is the reverse. So the equilibrium constant for this is simply going to be the reciprocal of Ksp. We are not going to do any actual calculations involving that particular equilibrium constant, but we are going to ask three questions, each of which involves the equilibrium expression and Ksp. And these questions are, first of all, if two solutions of ionic compounds are combined, will a precipitate necessarily form? Back in the introductory year of chemistry, we used our qualitative solubility rules to answer this question. As you will see, those rules are not always accurate. We need to do some calculations. Second question, if a precipitation reaction will occur, what will be the final equilibrium concentrations of all the ions? And then finally, what is the minimum concentration of ions needed in order for precipitation to take place? Here are some Ksp values in case we need them. So here's our first question. Will a precipitate form when a specified volume and concentration of magnesium nitrate is added to a specified volume and concentration of sodium hydroxide, for which I give you the Ksp value of magnesium hydroxide? So let's begin by writing out an equation to represent the dissolution and dissociation of the slightly soluble salt in question, magnesium hydroxide. Magnesium hydroxide dissolves and dissociates to form magnesium 2+ cations plus hydroxide anions, for which the Ksp expression is equal to the concentration of magnesium cations times the concentration of hydroxide anions squared, for which we have the numerical value 8.9 times 10 to the negative 12. Now, what we're really asking is the following. After we combine these solutions and dilute the initially given moles of magnesium 2+ and hydroxide to a new final value, will the resulting concentrations of the magnesium cation and the hydroxide anion satisfy the equilibrium expression? Well, we're going to do that by calculating those concentrations and then plugging them into Ksp to see if we are at equilibrium or not. This should sound kind of familiar. So, let's do some dilution calculations. Our initial concentration of magnesium 2+ is equal to the moles of magnesium 2+ that I'm starting with, divided by the total volume after mixing. Well, that's simply equal to the molarity, 4.0 times 10 to the negative 4th molar, times the volume of magnesium nitrate, 0.100 liters, over the total volume, 0.200 liters, or 2.0 times 10 to the negative 4th molar magnesium 2+. I'll do the same thing for the initial concentration of hydroxide. That will be equal to the moles of hydroxide that I'm placing in solution times, divided by the total volume, or 2.0 times 10 to the negative 4th moles per liter sodium hydroxide times 0.100 liters divided by the total volume, 0.2000 liters, or a value of 1.0 times 10 to the negative 4th molar hydroxide. So here are my concentrations immediately after mixing but prior to any reaction. So now, to determine whether or not a precipitation reaction is going to take place, I'm going to plug in the initial concentration of magnesium times the initial concentration of hydroxide squared times 10 to the negative fourth times 1.0 times 10 to the negative fourth squared, or 2.0 times 10 to the negative 12. What did I just calculate? By plugging in the initial, not necessarily equilibrium concentrations and comparing them to K? Yes, I calculated Q. And nobody ever calls it this, but it really should be called QSP, shouldn't it? Because it's kind of like KSP, except it's for Q instead of K. So let's take this value of Q that we just calculated and compare it to KSP. Q is 2.0 times 10 to the negative 12. KSP is 8.9 times 10 to the negative 12. So Q in this case is less than KSP. So we would predict that because the product of the concentrations of the ions is not high enough to satisfy the equilibrium condition, we would predict that no precipitation will occur. So even though KSP is pretty small, what do we say it was? 8.9 times 10 to the negative 12. Because the concentrations of the magnesium 2+ cation and hydroxide anion are not high enough to satisfy the equilibrium expression, no precipitation will take place. So what we just calculated is actually called the ion product. It is the value that you obtain when the initial, i.e. not necessarily equilibrium concentrations, are plugged into the KSP expression, and it is basically Q for this process. So if Q is greater than KSP, that means the concentration of ions is too large to satisfy the equilibrium condition. That means we must reduce the concentration of cations and anions in solution. How does that take place? Well, obviously by precipitation. So precipitation will occur, i.e. the reverse of the dissolution and dissociation process, until the concentrations are low enough to satisfy the KSP expression, which means a saturated solution is formed, and of course that means we are at solution equilibrium. On the other hand, if, as we saw in the example, Q is less than KSP, then the concentration of ions is not high enough and no precipitation will take place. So let's move on to the second question, which is, how do we calculate the equilibrium concentrations after precipitation? So here we're given volumes and molarities of potassium oxalate and barium bromide, and we are given KSP for barium oxalate. Let me write out the symbols of the ions. So the oxalate anion is CO4 2-, the barium cation obviously is Ba2+, and we're given KSP for that ionic compound. Well, we don't actually know that a precipitation reaction is going to take place yet. How do we determine whether these given molarities and concentrations of ionic compounds will form a precipitate? Just as we did before, we're going to calculate Q. So let's calculate the moles of the reactants present. So my moles of potassium oxalate will be equal to the volume times the molarity, or 0.0200 moles of potassium oxalate. And my moles of barium bromide will be equal to the volume times the molarity, or 0.0375 moles of barium bromide. Let's then calculate the initial concentrations of the oxalate anion and the barium cation. 1 mole of potassium oxalate gives 1 mole of oxalate anions, and I'll divide that by the total volume to give me 0.0800 molar as my initial concentration of oxalate after mixing but prior to reaction, and my initial concentration of barium 2+ is 0.0375 moles of barium 2+, because 1 mole of barium bromide gives me 1 mole of barium 2+, divided by the total volume, or 0.150 molar barium 2+. Notice in each of these cases, we had a 1-to-1 mole ratio of ionic compound to ion produced. If it wasn't 1-to-1, then you would simply have to use the corresponding mole ratio. So to calculate QSP, again, nobody calls it that, but they really should. I'll plug in my initial concentrations of barium 2+ and oxalate, 0.150 times 0.0800 is 0.012. Clearly, QSP is greater than KSP. which we said was 2.3 times 10 to the negative 8th. So we can conclude that precipitation will occur. So that's good. So now the question then is, what are the concentrations of all of the ions present after precipitation takes place? Well, clearly there's going to be some stoichiometry involved. So let's go back and look at the formula. We see that in the formula, in barium oxalate, BaC2O4, that the barium cations and the oxalate anions react in a 1-to-1 ratio. We're starting with 0.0200 moles of oxalate and 0.0375 moles of barium 2+, which is the limiting reactant. Oxalate is the limiting reactant, which means that barium will be present in excess. So let's do the stoichiometry and equilibrium calculations to see what's left. So our reaction that takes place is barium 2+ reacts with oxalate to form solid barium oxalate. Let's calculate the equilibrium concentration of barium 2+, which we said was the excess cation. So that will be equal to the 0.0375 moles that we started with minus 0.0200 moles that reacted. Why did that many moles react? Because that's how many moles of oxalate we started with, 0.0200, which we said is the limiting reactant, and they react in a 1-to-1 ratio. And I'll divide that by the total volume of solution, which is gives me 0.0700 molar barium 2+ present after the reaction takes place. Now, oxalate we said was the limiting reactant, which means it's all going to get used up. Does that mean that the equilibrium concentration of oxalate is 0? No, that can't be the case. If it were, that would imply that the KSP for barium oxalate is 0. It's not 0, it's small, so there will be some small equilibrium concentration of oxalate remaining in solution after the precipitation. What will govern the equilibrium concentration of oxalate? Why, the equilibrium dissolution and dissociation of the oxalate salt specifically, to give me barium 2+ plus oxalate, okay, as governed by the equilibrium expression. So I'll write out my KSP value. KSP is equal to the concentration of barium 2+ times the concentration of oxalate, CO4 2-. So essentially I'm asking myself, what is the concentration of oxalate present in a solution that contains 0.0700 molar barium 2+. It's essentially a common ion effect problem like we dealt with in the previous video. So I'm going to plug in here, and for my equilibrium concentration of barium 2+, I'm going to write S, and by the way, in this dissolution and dissociation, S moles per liter of barium 2+ and S moles per liter of oxalate are formed. S plus the 0.0700 molar that was left over, times S, the equilibrium concentration of oxalate produced in the dissolution and dissociation, which is equal to KSP, 2.3 times 10 to the negative 8. KSP is pretty small, 0.07 is pretty large, so I'm going to assume that any additional barium 2+ formed in this dissolution and dissociation is negligible. So, to solve for my equilibrium concentration of oxalate, I'll simply rearrange the KSP expression and plug in 2.3 times 10 to the negative 8 divided by 0.0700, or 3.3 times 10 to the negative 7 molar as my equilibrium concentration of oxalate. There's my result. Are we done? No, because the problem actually said calculate the equilibrium concentrations of all ions present in solution. What other ions are present? Well, of course, the potassium cations from potassium oxalate and the bromide anions from barium bromide, which are simply spectator ions. So, to do that, my equilibrium concentration of potassium are simply my initial moles of potassium divided by the total volume, and my equilibrium concentration of bromide will be my initial moles of bromide divided by the total volume, which is simple stoichiometry. I'm not going to waste your time by going through that. You could easily calculate that yourself. Okay, in the final section, we're going to ask about conditions required for precipitation. What are the minimum concentrations of ions present in order for precipitate to form? Here's an example. A solution contains 1.0 times 10 to the negative fifth, sorry, I'll come back to that later, 1.0 times 10 to the negative fifth molar sodium phosphate. What is the minimum concentration of silver nitrate that would cause precipitation of solid silver 1 phosphate? Pardon me, silver 1 phosphate, for which KSP is given. Okay, so we have a solution that contains one of the ions present in the precipitate, and I want to know what's the smallest amount of the other ion I need to add for precipitation to occur, i.e. for the equilibrium condition to be satisfied. Well, let's begin by writing out the equation for the dissolution and dissociation of silver 1 phosphate. My KSP expression is the concentration of silver 1 to the 3rd power times the concentration of phosphate. Well, I know the concentration of phosphate is 1.0 times 10 to the negative 5th moles per liter. So the question then simply is, what is the smallest concentration of silver plus that I can have that, when plugged into the KSP expression, will give me KSP, thereby satisfying the equilibrium condition, therefore resulting in precipitation? Well, all I really need to do is to rearrange and isolate concentration of silver plus, and then simply solve. Oh, what's that? Note to self, do the silver 1 chromate potassium iodide demonstration. Okay, let's do that in class. It's pretty cool. Glad I left that note to myself. All right, so to rearrange, silver plus equals KSP divided by the phosphate concentration raised to the power of 1/3 or cube rooted. KSP is 1.8 times 10 to the negative 18th. The phosphate concentration present is 1.0 times 10 to the negative 5th. I'll take the cube root of that, and I get a value of 5.6 times 10 to the negative 5th molar as my concentration of silver plus. So if my concentration of silver plus is below this value, 5.6 times 10 to the negative 5th, I will not have enough silver plus to satisfy the equilibrium condition, and I will not have precipitation. But once I reach that or exceed it, then I will have satisfied the equilibrium condition and precipitation will take place. That's pretty much it for chapter 6.